Hi, everyone. Okay, so for today, what I want to talk about is substructures, functors, and descriptive versus prescriptive signatures. And we're going to do this by extending the dictionary example that we were doing in last week's videos. So the idea of a dictionary, if you remember from lab last week, was that a dictionary is parameterized by a type of keys, a type of values. There's an empty dictionary. You can insert into a dictionary a key and a value to get a new dictionary that contains that key value pair. And you can look up a dictionary a key to get a value option, where option is either some or none, which says maybe the value exists, maybe it doesn't. And then both of insert and lookup take a comparison function. So they take a key star key to order, which is how you compare keys. So you can do dictionary stuff for any key type that is ordered. And then if you look at the videos from last Wednesday, we went over how to define a type of trees and then how to write lookup and insert for those. And so one problem that I want to point out with this is that if, for example, so we've got our comparison function, which takes ints, right? So there's a normal comparison function, int.compare xy, where if we compare 1 and 2, it says that 1 is less than 2. If we compare 2 and 2, it says that 2 is equal to 2. If we say compare 3 and 2, it says that 3 is greater than 2. But we could also write a different comparison function on ints. So we could write another compare, which is int.compare of y and x. So maybe you did something like this in homework 7 when you were trying to sort backwards. So if you do that, then if you do other compare of 1 and 2, it says greater, 2 and 2 are still equal, and now 3 and 2 are less because it's flipping the order. So one confusion is that you can get in your code is that imagine that we use our dictionary. So we say, let's make a little dictionary. We say treedict.insert with compare, the key 1 maps to A, and then we do treedict.insert of still with compare of that dictionary, the key 2 maps to B, and then treedict.insert of the same dictionary with compare, the key 3 maps to C. Let me see if this comes out how I want it to. Compare. Yep, sorry. C in quotes there. And then insert compare. Oh, forgot the empty dictionary. There. Okay, good. Okay, so now I've got a dictionary D. There's a little bit of magic. You might need to do this sometimes. If your trees are printing with hash signs in them, that's because it's not printing far enough in the tree to see what's really going on. So then we can do that. Okay, good. So now what I've got is a dictionary that has 1 in A at the top, 2 in B down the right tree, and then 3 in C there. Okay, that's not exactly what I wanted. Let me switch the order there and see if starting with that does better. Yeah, okay, good. Okay, so now we've got a dictionary that has 2 in B at the top of the tree, 1 in A to the left of it, and 3 in C to the right of it. So it's the balanced tree with 2B and then 1 down one side and 3 down the other. Okay, so now what happens if we look up with the compare function and we look up in D the key 2, then we get B. If we look up 1, then we get A. And if we look up 3, then we get C, which is what we would expect, right? If we look up the keys, then we get back the associated values. Okay, but here's a bug that you can make, which is that suppose that we look up with other compare in the same dictionary, the key 2, then we get our B, but if we look up 1, none. Okay, so why did we not find the value? Well, if a tree is sorted in a particular way, and then you use a different comparison function to look things up, we'll get a none for 3 as well, then what's going to happen is that you go down the wrong side of the tree when you're looking for the value, right? Because the comparison function tells you which way to go depending on whether you return equal, less, or greater. And if that equal, less, or greater doesn't mean the same thing as the comparison function meant when you created the tree, then you'll be in trouble because you'll go the wrong direction. So if we look up with the flipped comparison 1, it's going to tell us to go down the right subtree, and then we're not going to find the thing we wanted down the right subtree, and so we're going to get a none instead. Okay, so the problem here is that we're really should always be using the same comparison function for all the inserts and lookups. And so what we're going to do in a second is to talk about how to use something called substructures and functors in order to make sure that that comes true.